Hi everyone and welcome to this tutorial. My name is Tarini Bhatnagar and in the next 15 to 20 minutes, we are going to walk through a beginner-friendly introduction to machine learning using a real-world natural hazard dataset. Our goal over here is to build a model that predicts which earthquakes are likely to trigger tsunamis. And along the way, you'll see the complete machine learning workflow, starting with, raw data, the exploratory data analysis, all the way through training, evaluating, and interpreting a model. Even if you have never done machine learning before, you don't have to worry. Every concept has been explained from the ground up over here. You will also find interactive cells which you can change parameters and see what happens. So this is not a passive walkthrough, this is more like you experimenting with the model yourself. So before we begin, let's talk a bit more about the problem data set over here. So why do we care about these earthquakes and tsunamis? I'm sure everyone knows tsunamis are among the deadliest natural hazards on Earth. The 2004 Indian Ocean tsunami killed roughly 250,000 people, and the one in Japan in 2011 killed about 20,000. So here's the thing, not every large earthquake causes a tsunami. Whether one is triggered depends on a lot of factors such as magnitude, depth, location, and how the fault actually moved. So big offshore and shallow earthquakes with vertical fault motion are the most dangerous ones. But now where does AI fit into this? Real tsunami warning centers like the Pacific Tsunami Warning Center uses a combination of rule-based system, sensor networks, and expert seismologists. But machine learning can also support that pipeline by rapidly triaging incoming events, learning historical patterns, and providing a probability alongside the traditional yes or no decision. One important note upfront that I would like to make is that this notebook is entirely educational. This is not a real time warning system, but the workflow you will learn transfers directly to many other natural hazards and climate problems. So let's start. If you scroll down, let's look a bit at the background and prerequisites over here. So Google Colab comes pre-installed with most of the packages here. So you can just, sort of import using these cells. But if you're running the notebook locally and you might want to, install the packages before importing them, you basically just comment out these two lines, which, enables you to install these packages, and then you can sort of go ahead and import them into your local install. So any AI problem, any machine workflow starts with the data. Data is one of the most sort of important pieces of the workflow. You want to make sure your data is rich, it's of good quality, because if you have bad data that is being fed into your model, that means your model is not going to be of good quality. Garbage in, garbage out, as everyone says. So that is really true for machine learning workflows as well. So over here, for our data, we are using the USGS earthquake catalog. So that's United States Geological Survey. And so this is an global earthquake database that is maintained by USGS, which is free in public domain and covers every located earthquake from 1900 to today. So we are going to use every earthquake with magnitude of 4.5 or larger between 2015 and 2024, which gives us roughly about 8,000 events to work with. Each row has the event's name, latitude, longitude, depth, magnitude, and a few quality control metrics. The one that matters the most for us is the tsunami column. That's a flag USGS assigns after the fact to indicate whether an earthquake was classified as a tsunami relevant event or not. So this is going to be our target for today. That's the sort of variable that we are trying to predict. Now, if we scroll down a bit over here, where we talk about data download, now when we are actually running this cell would normally fetch the data live from the USGS API. But in Google Colab, that fetch sometimes fails due to many different reasons. It could be network policies or some other firewalls, etc. And in that case, if this happens, the notebook automatically falls back to a local CSV file that ships alongside this notebook. So either way, we get the same data. So over here is the first look at the data. The CSV that we are falling back to in case the live fetching of the data fails. So once the data has been loaded, we look at three basic things. And honestly, this step gets skipped way too often by someone who's beginning. So we have to look at the shape of the data. We need to know what does it look like, how many rows, how many columns, what are the different column types as well. So over here we can see the shape. We have about 8,000 rows and 19 columns. Second is the data types, mostly numeric, which is good for machine learning. And third, are there any missing values? Because real data sets always have missing values, and we can see ours has small amounts in the quality sort of control columns, like the number of stations and gaps, and we'll be handling those in a minute. Then we look at the summary statistics with describe, and notice that the minimum magnitude is 4.5, which is our filter. Depth ranges from near the surface to hundreds of kilometers. And crucially, the mean of the tsunami column is around 0.03, which means only about 3% of the earthquakes triggered a tsunami. And this brings us to one of the most important concepts in the whole notebook of, imbalanced data. So, this section is worth pausing on because it changes how we think about the whole problem. We just saw that our data set is imbalanced. 97% of the events are non-tsunami and only 3% are actual sort of tsunami warnings. Now, why does this matter? Because a lazy model can achieve 97% accuracy just by predicting a no tsunami column for every single event. That model would technically be 97% of the times correct, but it would be completely useless because it would never warn anyone about a real tsunami. So, we need better metrics than accuracy over here. The notebook explains these concepts using a simple fire alarm example. So imagine a smoke detector where 10 real fires happened in a year. The detector alerted 50 times total, but only 8 of those alerts were real fires. The other 42 were false alarms for from that burnt toast that you might have had. And two real fires that happened when they actually happened, the detector really stayed silent and did not sort of inform you. So from this we get to two metrics. Precision. Precision asks the question, when the detector alerted, how often was there really a fire? So in our example, 8 out of the 50 alerts were real, so precision is 16%. Low precision means lots of false alarms. On the other hand, recall asks the question, of all the real fires that happened, how many did we really catch? So we caught 8 out of 10, so the recall is 80%. Low recall means missed events. Now, these two metrics usually pull in opposite directions. You make the fire alarm detector more sensitive, you are able to catch more real events but produce more false alarms as well. On the other hand, if you make it less sensitive, fewer false alarms, but you miss a lot more real ones. So F1 is a single score, that combines precision and recall, and it is only high when both are high. Let's also talk a bit about the AUC ROC, which is a bit different, as it measures how well the model ranks positives above negatives across all possible thresholds. It tells you whether the model itself is any good, independent of where you set the decision cutoff. So with this, keep precision and recall in your head because they're going to come back over and over. And for tsunami warning specifically, we care most about recall because a missed real event costs lives, whilst a false alarm just costs public trust. So I want to pause here and sort of just repeat that, when I learned about these concepts, they might be a bit confusing. So I would, ask you to go over these concepts again, understand what accuracy means, what precision means, what recall means, what F1 means. These metrics are really helpful, but they can be a bit confusing. So it is definitely worth spending a bit more time trying to get the basics right. Let's now visualize the data. You can look at your data all you want, but the information provided to you by maps and, visualizing the data in different ways, that is just on next level. And I highly encourage you to start doing that. And that is very similar to, exploring your data at the beginning, like the shape and the describe. You want to visualize the data and see, what it tells you, what does it actually look like. So over here, we use the Folium library to create an interactive world map of all the events over here. The blue circles are non-tsunami earthquakes, whereas the red circles are tsunami triggering one. With this Folium map, you can zoom in, you can zoom out, pan around, and click on sort of any earthquake event to see more details about that. So take a moment to notice the patterns over here, and what you'll see is that most of the earthquakes cluster along the tectonic plate boundaries. So, what we have seen is tsunami triggering earthquakes concentrate especially in the Pacific subduction zones and around Indonesia. Next, we look at the distribution of the magnitude and depth. Magnitude follows what's called a Gutenberg Richter distribution. Lots of small earthquakes, very few big ones. Notice the y-axis is on a log scale because otherwise these small earthquakes would completely dominate the picture. And the depth is bimodal. Most events we see are shallow, but there's a smaller cluster of deeper events as well. Then we get to what's probably the most important sort of plot in the whole notebook, which is the tsunami rate by magnitude. What we can see is below magnitude 5.5, tsunamis almost never happen. Between magnitude 6.5 and 7, about 1 in 4 event, trigger a tsunami. And above 7, the majority, events trigger the tsunami. Now, this is a huge signal. It tells us that magnitude is going to be a very strong predictor for our model. If you look at the depth, we kind of see the same story over here. Very shallow earthquakes are much more dangerous than deep ones, which matches the physics. Deep earthquakes don't move the seafloor and hence triggering the tsunami. So the try it yourself part over here lets you experiment with different magnitude thresholds. This is a great place for you to pause and play with the code and see how the plots changes and what kind of story does it tell you. Okay. Now with the features and target, how do we define these variables? The first step over here is to handle missing values. Remember, in the notebook at the beginning, we did see that we had a lot of missing values over here. We need to fix that. And the easiest way to handle missing values over here is with median imputation, which is very simple and a sensible default to fall back to. So what we do is in the code over here, we just basically, ask the sort of code to fill in the median values wherever there's a missing value. Then, comes something that trips a lot of people. How do we encode location? And we did see, in the map that, location is also a very important sort of feature over here. You might think we can just use latitude and longitude directly, but there is a subtle problem over here that longitude wraps around. What that means is, longitude 179 east and longitude minus 179 east are almost the same place geographically, but they're just across the international date line, near Fiji. But numerically, if you would see, they are 358 units apart. Now, if we feed the raw latitude and longitude to a model, it would think that these two Fiji locations are on opposite sides of the world, but in fact, they are very close to each other. So the fix over here is to compute two features instead of one, the sine and the cosine of the longitude in radians. Now, this transformation puts every longitude on the unit circle, so nearby locations on the globe correspond to nearby points in the model's feature space, even across the wrap. So the notebook over here shows this with a concrete example. When we compute the cyclic distance between Fiji East and Fiji West, we get around 0.03, which is very small and it matches reality. Between London and Fiji, we get about, let me scroll down, to 2.0, which is large, but also matches the reality. So this means our transformation is working. Now we apply the same trick, to the latitude for consistency. And we add one more feature, which is a Boolean flag, called shallow, which is if depth is under 70 kilometers. Now, this makes the shallow versus deep distinction explicit for the model. And one sort of final feature, our final feature set has, 11 features over here: magnitude, depth, shallow flag, the four cyclic location features for latitude and longitude, the four quality control metrics, and this target feature over here is the Tsunami flag. Okay, now let's go to the data split. Before training anything, we need to split our data, and we used 3 splits. So, why do we exactly need to split the data in the first case? So, we cannot evaluate a model on the same data that has been, trained on, because the model has, seen those examples and will make itself artificially look good. So we need to train the model on, a separate data and then sort of evaluate your model on a separate data set to actually see how good of that model it is. So the training set, which is around 60% of the data, is what the model learns from. The validation set, which is around 20%, is what we use to compare different models and tune the hyperparameters, turning those small knobs to make sure our model is performing good. And then finally, the test set, that's the final 20%. This is a set we hold out completely, and the model only looks at it once and at the very end for an unbiased estimate of the real world performance. Because out there in the wild, once you have your model trained and your model will be sort of, performing and taking in the data set that is coming in, that is data that the model has never seen. So now we need to make sure that our model has been trained on good data sets, so that now out in the wild, when it sees new data, it is actually, holding its weight. So why do we have three splits and not two? As we discussed, because if we tune our model based on test performance, we are effectively training the model on the test set, and its measurement is no longer reflecting real world performance. So here the validation set gives us somewhere to experiment, and the test set stays untouched. So one important detail over here is that we, pass stratify equals y to the split function. Because tsunamis are so rare, a random split might accidentally put most of the tsunami events in one split by chance, making the evaluation unstable. We want to make sure that, our stratified sort of different data sets have the sort of same number, same ratio of tsunami events as well. So you can see in the output that all three splits have around, 2.6% tsunami events. And that means that your stratification is working. So now let's start working on building a baseline model. So before, training a fancy machine learning model, we always ask, how well would a really simple approach do? If our sophisticated model cannot beat common sense, then we might as well just use the simple approach, right? So over here, we are comparing two baseline models. The first one is always predicting no tsunami. Now this gets 97% accuracy by ignoring the data completely. Remember, we saw there were around 3% of tsunami events. So now if we have this model that just says no tsunami at every event, then we are actually getting an accuracy of 97%. Now this is including specifically to prove that accuracy is a terrible metric here, and you can hit 97% and be totally useless model. The second baseline model is a simple rule from seismology. Here we are flagging events where magnitude is at least 7 and depth is under 70 kilometers. This kind of captures the physics we saw earlier, that big shallow earthquakes are the dangerous ones and we need to flag those. So the second baseline model is the honest bar we need to beat with our machine learning model. If our machine learning model cannot do any better than this, we don't actually need any machine learning over here. So over here, there are cells like, you can play around with different magnitude and depths. So you can change the threshold and, try different values and see what happens to the precision and recall metrics. Okay, so now we actually train our first machine learning model, which is going to be a logistic regression, which is the simplest classifier that actually learns from the data. So one important pre-processing step over here is scaling the features first, because logistic regression is sensitive to features being on wildly different scales. Notice we fit the scaler only on the training data and then apply the same transformation to the validation and the test data set. Fitting on the full data set would leak information from the test into the training, and that is not what we want to happen. So we also, pass class weights equal balanced, which tells a model to, care extra about the rare class of the tsunami events. And without this, it might just learn the lazy, predict no tsunami strategy that we spoke about. Let's see how our model actually did. So first, the raw numbers. Our logistic regression hits about 93% accuracy on the validation set. But as we discussed earlier, accuracy is misleading for imbalanced data. Remember, always predicting no tsunami would already give us 97%. So the numbers to watch is recall, which comes in around 97%. That means the model is catching almost every real tsunami. On the other hand, precision is lower, around 28%, meaning many of our alerts turn out to be false alarms. And F1 sits around 0.44 and AUC is around 0.98, a strong signal that the model ranks tsunamis above non tsunamis very well. Now, let's look at the bar chart comparing our different models over here. So it compares the three approaches. The gray always predicts no tsunami baseline, the orange rule based baseline, and the green logistic regression across the four metrics that we just discussed. Look at the accuracy bars first. The use this always no baseline actually has the highest accuracy, as we saw earlier, and that single bar is why we don't trust accuracy for this problem. Now look at recall. Logistic regression shoots up to near 1.0, while the always no baseline sits around 0. It never catches any real tsunamis. So this is the metric that matters for a warning system. The trade-off here appears in precision. Our model has lower precision than the rule baseline. That's the cost of aggressively catching real events, that we produce more false alarms along the way. Now, if we scroll down a bit, what you are looking at over here is called a confusion matrix, and it shows you, all the sort of different number of events for the true label as well as the predicted label. So it's a 2x2 table showing 4 outcomes: true negatives, non-tsunami correctly identified, a big number. Then on bottom right, we have true positives, which are real tsunamis caught. Top right, false positives, false alarms, and bottom left is false negatives, which is real tsunamis that we missed. Now, these are the dangerous errors. You can notice over here the false negative count is very small, while false positives are much larger. And that asymmetry is by design. We use balanced class weights, especially to push errors away from false negative box, because for tsunami warning, a false alarm costs trust, but a missed tsunami costs life. So we cannot afford to miss a tsunami warning. That is more important than providing a false alarm in some cases. Okay. The next important concept that I want to walk through is that of, overfitting over here. And this is also one of the most important concepts in machine learning. So overfitting is when a model learns the training data too well, including the random noise that is included in the data set. With this, the model actually performs beautifully on the data it has seen, but very poorly on the new data, which is not the ideal situation for us. You can think of this as a student who memorizes exam answers instead of understanding the material. So they're able to ace the practice test, but they fail the real exam. So the clearest way to see overfitting is with a decision tree. If you let a decision tree grow deep enough, it can memorize every training example perfectly, and presents the classic problem of overfitting over here. So let's watch what happens over here. We train the decision trees at 9 different sort of maximum depths, from 1 all the way up to sort of unlimited depth. And then we plot the training F1 versus the validation F1 for each over here. Look at what happens. So the shallow trees at depth 1 or 2 are underfitting. Both scores are low because the tree is too simple to capture the patterns present in the data set. But now when we move on to medium depths around 3 to 5, both training and validation F1 sort of rise together. This is the sort of sweet spot. But at depth 15 or unlimited, training F1 climbs to 1.0. The tree has memorized the training set completely, while the validation F1 actually drops. This widening gap between the blue and red line is overfitting, and this is, telling us exactly over here that our model is learning the random noise and the training data too well, but when it actually goes out to perform on the real world data set, it is actually performing really poorly. So the model looks great on the training data, but has learned patterns that don't generalize, in the new data set. So this is exactly why we need a validation data set. If we only looked at training performance, we'd think the deepest tree was the best, but the validation set actually reveals the truth about your model. We looked at the patterns, between how the F1 accuracy changes between the validation and the training data set. So it is very important that you think about overfitting and look at ways how to prevent overfitting as well. Some of the standard techniques that you can employ that I'm not going to go into more details, like this is more for your knowledge, is that you can limit model complexity. You can set a maximum tree depth or use fewer parameters. You could use regularization, which is where you mathematically penalize a model for being too complex. That is built into logistic regression. Or you can have more training data, which makes memorization much harder. Or you could have different ensemble models, where you combine different models to reduce overfitting. Or there's also a technique called early stopping, where you stop training while when validation performance stops improving. So it's worthy to look at these different sort of methodologies, not just for this notebook, but in future as well. Like, this is an important concept to think about. So over here, you can try it yourself, pick a tree depth and see how the performance is both on training and validation data. And your goal over here is to find the depth that gives the best validation F1 without a large training and validation gap. Okay, and then there's a challenge over here, like can you improve the model using different techniques such as adjusting decision threshold, trying different model hyperparameters. And this is a technique you'll see, like it's never a one-time process that you train a model and it's done. You always have to look at the model performance. You have to turn different knobs, change in different model parameters, and basically your goal is over here is to find that ideal set of parameters that is giving you the best performance. And you'll find yourself adding, removing features, or trying a different approach, different algorithms as well. So you need to find that sweet spot, and there's a lot of experimentation involved, a lot of iteration involved in this process. So this is the moment of truth. Up until now, we have been comparing models on the validation set, and the test set has been held back the entire time. You remember, we have been using our training and validation set to come up with the best hyperparameters to choose the models, and the test set is the final evaluation set that the model has not seen before. We look at it exactly once, and we don't tune anything afterwards, because otherwise we are effectively training on the test set as well, which is not what we want. So once we have this code to have the final test set performance, let's look at the numbers. The output has, 4 rows corresponding to the rule baseline, the logistic regression, our best decision tree, and the challenge model you built. And let's, read them together. So the rule baseline, which was magnitude 7 or more and depth under 70 kilometers, posts an F1 of around zero point 0.5, which is not bad for a two-line rule. And this is the honest bar our machine learning model needs to beat. Now, if you look at the logistic regression model over here, the F1 is around 0.42 to 0.44, with a recall of nearly 0.97 and precision of around 0.28. On F1 alone, it's actually a bit worse than the rule, but look at that recall. We are catching almost every real tsunami over here, and that matters. So, depending on how much you value avoiding missed events, that trade off might exactly be, the thing that you want. The decision tree, at its best step, the one we choose from the validation curve, falls somewhere between the two, usually with a better balance of precision and recall. And the challenge model, which is typically, a random forest, usually posts the highest F1 of the four. That's the ensembling advantage. Like many trees voting together are more robust than any single one. The key thing to notice over here is that the numbers on the test set are close to what we saw on the validation set. That's a good sign. It means our models are generalizing and not overfitting. If the test performance had suddenly collapsed, that would tell us that we'd been fooling ourselves because the model basically learned everything, all the patterns in the training data set. And, we could not be confident that the numbers reflect the actual performance anymore. So finally, we look at what the model has actually learned. So for logistic regression, the coefficients tell us which features drive the prediction. As expected, magnitude and the shallow flag are the strongest positive drivers. Big shallow earthquakes raise tsunami probability. That matches the physical intuition, which is reassuring. If the model relied on something suspicious, like the number of stations, that would be a red flag. So, with these models and looking at the predictors, you know, it has to make sense. So, over here, you can see that it matches our intuition, and this would be a place that would tell you if your model is, maybe looking at completely the wrong features and you need to fix your model about that. So once you have done that, we can see the different sort of accuracies, the different sort of important predictors, the the metrics, and see if our model actually performed better than the baseline models that we came up with. So there are definitely some data limitations and modeling limitations that I have listed out here. And this is going to be true with any kind of data set. So it is important that you note these down. You make, anyone who's using your model aware of these limitations so that, they can take these and sort of, have these interpretations um, that take into consideration these limitations. And of course, before any real world use, a system like this needs, some sort of expert review, such as, qualified seismologists must validate alerts before a public release, and real time sensor integration, equity analysis, etc. There are some reflection questions for you, and if you're up to it, there are extra challenges as well. You know, which helps you sort of play with different models, parameters, and predicting maybe different features, not a tsunami event but predicting a magnitude instead using different features. So I encourage you to take advantage of this. So yeah, that's the full workflow. And in under 2 hours, you've gone from raw earthquakes data set to a trained and interpreted machine learning model while you're learning every concept along the way. The most important sort of takeaways over here, as I would say, are that always look at your data first, always build a baseline model, and always be suspicious of accuracy and imbalanced problems. And do check the training versus validation performance to spot overfitting. Now, there's a link at the bottom of the notebook for sort of where you can find this data set, and the documentation, more sort of notebooks as well, more advanced if that is something you want to explore. Now, thanks for watching, and coming along with me in this journey. If there are any questions, feel free to reach out to me, and I would be more than happy to help you out. If you're stuck anywhere or if you need any sort of explanation. Thank you so much, and I hope you have a good time, learning and going through the concepts over here. Thank you again.